Alright, so I have a potential energy problem for us. I mean, it's not exclusively potential, it's kind of mechanical, it includes some other things. However, you'll see it's a key role. So our problem is that a biker of mass 95 kilograms is going down a 7-degree incline, well, the hill's 7 degrees at least, and the distance of that hill is going to be 620 meters. To make this a little bit more, fun, I did add a frictional force of 75 newtons. This will just show that the energy is not always conserved, you kind of lose off a little bit. But yeah, here's our diagram. I have the biker going down the hill. The name of the vector I just put is f of g because it's kind of, the gravity accelerator that's making them go this way. And the only force acting against is that frictional force. So I do have our theta put in, our distance, and the height is right there, but we'll get to that in a second. All right, so the biker does start at rest. So he has no kinetic energy. All the energy of him is going to be potential, and potential energy is going to be equal to the mass times the gravity accelerator times the height. I do have the height in a different color because we don't know it. So using some trigonometry, we know that sine of this angle is going to be equal to opposite over hypotenuse. And I am looking for the height, so I called that opposite. You'll see I'll plug that in a minute. So sine of the 7 degrees is going to be equal to opposite over hypotenuse, which is 620. If you just multiply that to the other side, you'll have sine of the theta times 620 equals the height. Working that out, you'll get 75.56 meters. And I do plug that in, all those right there. So the potential energy is going to be 70,346 joules. A lot of energy, I know. So this is our initial energy. Like I said, there was no kinetic energy because it did start at rest. And if you wanted to write it in terms of, the final energy, so the initial energy is going to be equal to the final energy or the total energy minus the energy, I guess, wasted, or the frictional energy, like the work by friction. And just rewriting that just to keep the, put the final energy by itself, we have the initial energy plus the work done by friction is equal to the final energy. So we do already know the additional energy. Like I said, it was just potential energy, so we can go ahead and plug that in. Minus, so the work done by friction is just going to be the frictional force times the distance upon its acting. So it's just going to be the 75 for the frictional force times the distance, was the 620. Plugging that in, you'll get the 70,346 potential energy minus the 46,500, which is the work energy of the friction, is equal to our final. So our final energy is going to be equal to 23,846. All right, so since the initial energy was all potential and he's just going all the way down, at the bottom of this, all of that energy is not necessarily converted to kinetic energy, but it is in motion now, so it is kinetic energy. The reason I said it's not necessarily is because, some of it is lost due to this friction. So what I did here was that I just changed the variables to kinetic energy because the final energy is just kinetic energy. And we also have known that kinetic energy is equal to 1/2 mass times velocity squared. All right, so we just, plug in all of the variables we know. Our final energy here is equal to the 1/2 times 95, which is just 47.5. I just divided that out to take them on each side. And you'll be left with the velocity squared is equal to 502.602, yeah. And take the square root of both of those, and you'll be left with 22.4 meters per second is the biker's final velocity.